be moving back towards it. So anytime we have this, we go to a point. If the div is positive, then we call that point a source point, because things are wanting to move away. So it's like you're at a campfire, you can feel the heat coming off it. It's a heat source, things are coming out of it. So when your div is positive, things are coming out of the point, it's a source. If your div is negative, then things are wanting to go in, that's called a sink. And anytime your div is 0, it's called incompressible. And the idea is, that it, like a solid block, nothing wants to go in, nothing wants to go out. There's equal going in than there is going out, so it's just kind of static, right? Incompressible. Now the computation of div is much easier than the computation of curl. So easy, in fact, that I can just do one example and we can move on. So div, the notation for it is this, div f. It does involve del again. There's del. That's a differential operator. But instead of crossing it with f, we dot it. And we like dotting vectors, right? Dotting vectors is so much easier to do. So if I take, I don't think I have it written here, but this is del. Right? That's del. And this is f. P, Q, R. Then if I dot them, I do this and this together, right? Which means the partial of P with respect to x, because it's a dot product, plus partial of Q with respect to y, plus partial of R with respect to z. So it's super easy. All you're doing is taking the derivative of each of these component functions with respect to x, y, and z respectively and adding them together. And that's it. Your answer is a scalar. That's the problem we had earlier, where we were asked to find the curl and the magnitude of the curl. Remember that one? That took us a little bit. Let's do div. Div f is del dot f, which is, I'm just going to do this without writing the formula. It's the partial of this with respect to x. 2x, y, z. Vector? No, plus partial of this with respect to y. 2x, y, z, plus partial of this with respect to z. 2x, y, z, which is 6x, y, z. That's your div. So the div of this particular vector field depends on where you are, right? Your x, y, and z coordinates all contribute to whether or not you're going to have div or not. Now at the point 2, 1, 0, what's your div? 0, because the z is 0. We happy? Now, this is going to look weird. But remember Green's theorem, right? Remember Green's theorem? Yes? Green's theorem says that the line integral along closed curve C, P dx plus Q dy is equal to double integral over the region D that C encloses of partial Q with respect to x minus partial P with respect to y dA, right? That's Green's theorem. But this, oh, and this right here, sorry, this is equal to line integral over C of f dot dr. Do you agree with that? This is this, yes. Which is this. So look at this new formula for Green's theorem. If this is equal to this, right? That's equal to this. That means that this right here, oops, I thought I silenced that, must be equal to this right here. Do you agree with that or not? Yeah, what's the curl of f? Well, let's go back in the notes real quick. curl of f. Where are you? There it is. Okay, there's the curl of f, right? If I dot that with k, because that's what that formula said just a second ago, dot that with k, what's the k vector? IJK? 0, 0, 1, right? If I dot these, the 0 kills off the first one, the 0 kills off the second one, and 1 times this is that, right? It's another way of writing Green's theorem with all vectors in it instead of having this right here. These are scalar functions, right? So that's why we call that a vector version of Green's theorem. Okay, understand? That will come into play later. And the next one for sure is going to come into play later. It's another way of writing Green's theorem. All right? And for now, what I want you to do is just remember this is here. I'll refer back to it later. I don't want to derive this. The book does it. They do a decent job. I want to spend some time. I would want to spend probably 20 minutes to 30 minutes deriving that and making sure you understand where it comes from. I'm not going to take the time. Just later on when I refer back to this, right, have a little note somewhere that says, you've got the formula sheets, right? Yeah. You got this in there, all right? Now there are a bunch of identities with curl and div, and I have one here that I'm not going to work through. I just want to show you like the basic idea behind it. If you take the div of the cross product of two vectors, it's equal to g dot curl of f minus f dot curl of g. And this is an identity. And do you remember in pre-cal when you had to show an identity, like you started with one side and turned it into the other side? That's what you would do with this. And this is in your notes. You can follow this. They started with the left side, and they turned this into the right side. All right? I think what I'll do is you almost had one of those on your take-home, but I took it off. It was the last problem. I took it off. I might offer that as an extra credit, or maybe something to that effect on the final as an extra credit, without ever showing you how this is done. See if someone would want to tackle that. Now, your homework assignment has a few of these. I think there's 2 of these, which I did not put solutions up for. Again, those, just realize those are going to be bonus problems, so you don't have to do those. There's the homework. I'm talking about 21 and 23 are identities. All right. That's it. We doing all right? 3-5? It's pretty straightforward, 3-5, right? It's just computations.
So just 6, 7, and 8 more?
Pardon?
13, 6, 7, and 8, that's it?
13, 6. Oh, yes. No, there's a section 9, I believe. Maybe not. Yeah, there's 9. But section 9 is only 3 or 4 pages long. All right, we are going to start 3, 6, but not heavily. I'm just going to get you going with this, and then I'm going to have a handout. We're going to start talking through this handout. Okay, remember, way back from chapter 10, look, this is a really important section, all right? I lose a lot of students right here in this section. So ask me questions. When I hand you this handout in a little while, if you have questions, let's resolve those, because if you can't do what's in this section, the next 3 sections are going to be impossible, because you have to be able to do what this section asks you to do. All right, remember from chapter 10 that if we defined a vector function r of t to be f of t, g of t, or if we do it three-dimensionally, then this drew a curve. And I told you back then that later on we would be able to do something like this and be able to draw surfaces. And that's what this section is about. Can we draw a surface with a vector function? And the answer is yes. Okay? If we have a vector function, and this time, instead of having one variable that we're plugging in, t, we plug in two variables, which we call u and v. I'm going to write this over here because it's going to be so important to us. If we have two variables being plugged in, and then a three-dimensional vector, okay, where the x somehow depends on u and v, the y somehow depends on u and v, and the z somehow depends on u and v, then if you define it that way, and you let you put some restrictions on u and v, give them some domain restrictions, then you will draw a surface in three-dimensional space. The book does not take a lot of effort and time in letting you practice converting a surface into that form. So that's what I would like to do now. I'd like to hand you this worksheet, and we are going to go through, and there's, I think, examples A through F, and we're going to come up with these parametric functions. It's called parametric surfaces. Go ahead and hand those all the way back. You know what? Let me get you two more. Whoa. If you could hand those back, please. 5. There you go. These are hard to see from the drawings. I don't believe that this is up. Someone can tell me, is there a CDF file on the website that has this? It's hard to see with what you have in your hands, so no, you can tell me later. Okay, you ready? I want us to come up with a parametric surface. In other words, a function R, a vector function, which depends on two variables u and v, that will draw me that circle. So let's pay attention to what's happening here. This circle lies in which plane? I did label x, y, and z on yours, right? It lies in the xz plane. So if I look at it, okay, if I twist this around like this, kind of turn it, come in like this, then do you see that I have a positive, this is the x direction, positive x direction, this is the positive z direction. And so what I need to do is just draw a disk, right? A solid disk in the xz plane. Okay, so let's talk about the different parts of this. Your x, your y, and your z. Right now, you know, because of where you are, any point that lies on this surface, the y value is 0, right? That'll flatten it out onto the xy plane. Agreed? Xz plane, sorry. We agree? So this is definitely 0. The other part of this, the x and the z, need to draw you this circle. Well, actually, it's not a circle, it's a disk. You have control of two variables, u and v. You can control them however you want. So just what does your instinct tell you you're going to need in order to draw something like that? Cosine and sine. Now, we've used cosine t and sine t, right? This time we don't have t, we have u and v. So how about this? How about cosine u, sine u? If I let u vary between 0 and 2 pi, this will draw me a circle with radius 1 right now, right? Right? But I wanted to draw a circle with radius 2 and 1 and 1/2 and 1.5 and everything in between. So I want to be able to vary that radius. And I have another variable. So why don't I let the number in front of this be v, and then control v with this inequality. Do you understand how that worked? Okay. So if you wanted to check whether or not you did it right, what you could do is you could say, okay, let v be 0. Start here with v is 0. V is 0. These are both 0. That's everything is 0, right? And you get the point 0, 0, 0. Good. It's there. Then you could let, I don't know, v be 1. If v is 1, and now let u change, you draw that unit circle. If you let v be 2, that'll be 2 and 2, and then you draw a circle with radius 2. Understand? And then everything in between. I hope that makes sense. That's the easiest one. No questions. Let's look at B. Find the vector functions, plural, which yield the 4 face surfaces of the tetrahedron with the given vertices. So you have a tetrahedron. It has 4 faces on it. Since each of the faces is a surface, you have to come up with 4 separate parametric functions that draws each surface. Here it is. Mine looks a little different than yours, but there it is. So let's start with the easy surfaces first. Let's look at the surface. Well, you tell me, which one do you want to start with? The base of this tetrahedron, which that surface lives in the xy plane. Agreed? The base of that tetrahedron. So I'm going to draw my xy plane like we normally look at it. Here's x, here's y. And give me some points that are on my tetrahedron that I can put here. That, I believe that is a 3. Yeah, well, yeah, I gave you the vertices, didn't I?
Yeah.
I didn't label them, though?
No, but yes.
It's 3. So this point is out 3, 1, 2, 3. So this would be a 3 here. And then 4 on the y. And then, of course, the origin. So we're talking about this surface. I want you to be able to draw that. And you can control 2 variables, u and v. Well, this looks a whole lot like a type 1 region from double integrals, doesn't it? And since it looks like that, we did this already where we controlled, what, x and y? This was type 1. We let x go between 0 and 3, and we let y go between 0 and the function of x, right? This line. We're going to do the same exact thing, but we're going to use u and v instead. So I'm going to write this down. R of uv will be equal to, oh, is there anything about this vector function you can tell me right now?
Z is 0.
Z has to be 0. Because we're looking at the one that lives on the ground, right? So your z values are always 0? What do you want your x component to be? You want to call that u? Sure, we could have called it v also because we can control both of them. So I'm going to say this right here is going to vary back and forth. That's going to be my u. So that's this. U then would be between 0 and 3. Now I have to get control over the v and figure out how it plays into this. This is the part that most people get hung up on. What are you thinking? If this is really my u now, right? Right? That's really my u. Then this right here, my y, what is this equation for y of this line? What's the slope of it? Negative 4/3 u, right? Plus 4. That's the equation of this line. Y-intercept 4, slope negative 4/3. Yes?
Yes.
Here's the mistake that people will make. what they will do is say, oh, okay, well, that tells me what my y is, right? So my y is negative 4/3 u plus 4. They put that there. Why is this incorrect? Pardon that? Pardon me?
You need to be in terms of u.
Well, it is in terms of, we haven't used v, right? If we haven't used v, then this is a function of one variable. And if this is a function of one variable, it doesn't draw a surface. It draws a curve. What curve is this drawing? It's just drawing this line. See, because what's happening is that if I fix u to be 0, what's this? 4, right? So I go 0, 4, I draw that dot. If I let u be 1, let's let u be 3. If I let u be 3, then where am I? 0. So I'm over here. I have no choice. Let's let u be 1. If I let u be 1, where am I? Let's see, negative 4/3 plus 4. I'm right there, okay? But I'm drawing the line. I'm not drawing the actual surface. What I need instead is that when I'm at u equals 0, I don't want to draw just that point. I want to draw every point between here and there, right? And when I get to 1, I don't want to draw just that point. I want to draw every point between this and that point. Yes? So what I do instead is I call this V, and I control V down here by letting it vary between 0 and negative 4/3 u plus 4. Extremely different thing happening here. Do you see the extreme difference? Okay, let's run through it again. Someone comes in right now and fixes u at 0. That's a 0, right? What's your v? Your v is going to be between 0 and, put 0 in here, 4. So when your u is 0, your v is everything between 0 and 4, so it draws that entire vertical line for you. Then you move u over, let's say we move it to 1. Move it to 1. Now my v is trapped between 0 and whatever that number was. It's going to draw everything between 0 and all the way up to that line. That's supposed to be straight. Understand? And so as I move u across, my v keeps adjusting, and I draw all the vertical lines, and I draw the entire surface. Okay. Let's see if you can come up with the parametric equations for the remaining two outsides. So we just did the bottom, right? We just did the bottom. Can you do this back side back there? Or the back side of that one? See if you can do it on your own. You can use u and v again. Okay, this is a totally separate surface. All right. And let's call these something. Let's call this surface A. Let's call the one over here B. And the one on this back side, let's call it C. That way we're all on the same page with this. So everyone try B right now. Anybody think they have it yet? Okay, you think you do? Okay. If you think you have it, try and get C. If you think you have B, you can look up at the board. That should be what you have for B. So here's what I'm going to do, because we've got about 5 minutes. I don't want to end early, but I also want you to kind of explore this on your own a little bit. I'm going to make for a take-home assignment that is due on Monday, all right, is just to do C, and there's one more surface, which we've conveniently avoided, which is this one up, that's the face, right, of this thing. That's the hardest one. I want to see how you do trying to get that yourself. Do you want any hints, or you want a couple of hints? It's a plane, and so there is a relationship between the x, y, and z. If you could figure out what the equation of the plane was, you would have that relationship. Then it's just a matter of making sure you get all this right. So I will see, everyone should be able to do C. I've shown you one. I've given you the answer for one. Hopefully you can get the last one yourself. This front face, which we'll call D, let's just call it D, which is this face right here. I'll just see what you do, all right? Say that's due Monday, beginning of class. All right, we will pick up next time. We will go through and finish off the rest of the examples on this, and then we will get into the next section, which is surface integrals. We're going to be not surface areas. We're going to be integrating where our region of integration is a surface instead of a solid. So that'll be interesting. Then we get to flux, and then the Stokes' theorem, then divergence, and then divergence theorem, and then we're done. Have a good weekend. Stay out of trouble.